In the first fraction of a second after the Big Bang, the universe was too hot and dense for any particles or atoms to exist. It was filled with quark-gluon plasma, a state of matter in which quarks, the fundamental particles that later formed protons and neutrons, were not encased in atomic nuclei, but were in a free state in a soup of gluons, particles mediating the strong force holding quarks together. As the universe expanded and cooled, it reached a temperature at which quarks could combine to form protons and neutrons, the building blocks of atomic nuclei. This epoch, known as the Hadronic epoch, occurred within the first microsecond to 1 second after the Big Bang. The formation of protons and neutrons was a turning point in the early universe, laying the groundwork for the creation of more complex forms of matter. After the Hadronic Age, the universe continued to cool, leading to the Lepton Age, which lasted from 1 second to a few minutes after the Big Bang. At the time, leptons, like electrons, were the dominant form of matter. The universe was still too hot for protons and neutrons to combine with electrons to form a nucleus. The most important particle formation event took place: nucleosynthesis, a process that occurred in the first few minutes after the Big Bang. During this time, the universe cooled so much that protons and neutrons began to combine to form the nuclei of the simplest elements: hydrogen, helium, and small amounts of lithium and beryllium. Primordial nucleosynthesis produced most of the helium in the universe, along with hydrogen that had not bound into helium nuclei. It is important to note that these were not yet full atoms as we imagine them today. Electrons orbit around a nucleus. The universe was still too hot for electrons to be captured into orbits around nuclei to form neutral atoms. The formation of neutral atoms, a process known as recombination, would not occur until 380,000 years after the Big Bang, leading to the separation of matter and radiation and the emission of the cosmic microwave background radiation. The afterglow of the Big Bang gives us a glimpse of what the universe was like at that time. Now, let's delve into that exciting era, when the fundamental forces of nature began to delineate and define the evolving cosmos. This history of separation is a cornerstone in understanding the complex tapestry of the universe, from its most nascent moments to the richly structured space we observe today. Initially, in the first moments of the universe's existence, all the forces were combined into a single force, indicating the extreme conditions of temperature and density that the cosmos was under. As the universe expanded and cooled, this primordial unity split in a series of symmetry-breaking events, giving rise to the various forces we know today: gravity, electromagnetism, strong nuclear forces, and weak nuclear forces. The first to separate was gravity, which emerged as a separate force when the universe cooled from its incomprehensibly hot and dense state. This separation is hypothesized to have occurred just a fraction of a second after the Big Bang, marking the universe's first step toward the complex force interactions that govern it now. The separation of gravity laid the foundation for the large-scale structure of the cosmos, directing the formation of galaxies, stars, and planets, forming the very fabric of the universe. After gravity split, the great unified force, which included the electromagnetic strong and weak nuclear forces, remained in its unified state until the universe cooled further. When the temperature dropped to a critical point, the strong nuclear force, which is responsible for binding quarks within protons and neutrons and maintaining the integrity of atomic nuclei, separated from the electroweak force, which is a combined form of the electromagnetic and weak nuclear forces. This separation, which occurred about 10 circles 36 to 10 circles 32 seconds after the Big Bang during the epoch of cosmic inflation, laid the groundwork for the formation of the first particles of the universe. Electroweak forces continued to govern the energy landscape of the universe until they, too, underwent symmetry breaking. As a result of this event, which occurred about 10 near-flexible 12 seconds after the Big Bang, the electroweak forces separated into the electromagnetic forces mediated by photons and the weak nuclear forces responsible for radioactive decay and nuclear fusion processes in stars. This separation finalized the composition of the fundamental forces, creating the conditions for further cooling of the universe, which allowed the formation of more complex particles and eventually atoms. The separation of the fundamental forces during the formation of the universe was a pivotal event that created the diversity of matter and structures observed in the cosmos today. Moving from the pivotal moments when the fundamental forces of nature began their gradual separation, we delve into the significance of the electroweak epoch, a defining period in the evolution of the universe. This epoch represents a critical phase shortly after the Big Bang, during which the electromagnetic and weak nuclear forces, two of the four fundamental forces, were combined into a single force known as the electroweak force. The electroweak epoch occurred roughly between 10 circles 12 seconds and 10 circles 6 seconds after the Big Bang, when the universe was cooling down from its originally hot and dense state, but was still incredibly energetic and dynamic. The significance of the electroweak epoch lies in its role in shaping the early universe and laying the groundwork for the formation of matter as we know it. In that epoch, the universe was filled with a hot, dense plasma of quarks, leptons, and their antiparticles, and electroweak bosons mediating a single force. As the universe expanded and cooled, it reached a critical temperature that allowed the electroweak forces to undergo a symmetry-breaking event. This event led to the separation of the electromagnetic force, mediated by photons, from the weak nuclear force, mediated by the WB and Z bosons. This separation was a fundamental step in the maturation of the universe, providing a diversity of interactions that eventually led to the formation of atoms and, by extension, the structure of the cosmos. The electroweak epoch has profound implications for our understanding of particle physics and the Standard Model. The Higgs mechanism, predicted by the presence of the Higgs field, played a crucial role in this epoch. The interaction of particles with the Higgs field endowed them with mass, a process that became central to the symmetry-breaking event that separated the electromagnetic and weak nuclear forces. The 2012 discovery of the Higgs boson, a particle associated with the Higgs field, was key evidence supporting the theoretical framework describing the electroweak force and its significance. Quarks, the fundamental constituents of matter, are subject to the strong nuclear force, one of the four fundamental forces that became distinctly apparent early in the evolution of the universe. This force, also known as the strong interaction, is surprisingly powerful, but its influence only extends over a very short distance. At the moments of the universe's birth, it acted as the glue that bound quarks together in groups of three, forming baryons that included protons and neutrons, the building blocks of atomic nuclei. This process began when the universe cooled enough for the strong force to overcome the kinetic energy that had previously kept the quarks apart. In this cooler but still incredibly hot environment, quarks began to interact more closely, forming pairs known as quark-antiquark pairs and triplets, which later evolved into protons and neutrons. The proton is composed of two top quarks and one bottom quark, and the neutron is composed of two bottom quarks and one top quark. The particular combination of quarks determines the properties of a particle, including its charge. Protons carry a positive charge due to their quark composition, while neutrons are neutral. This stage in the evolution of the universe involved not only the birth of these particles, but also with the transition from a state where quarks could move freely, the quark-gluon plasma, to one where they were locked into themselves: protons and neutrons. This locking mechanism is crucial to the stability of matter as we know it. Without it, the complex structures that make up the universe, from atoms to galaxies, could not exist. The hadronization of quarks into protons and neutrons laid the foundation for the next stage of cosmic evolution, the era of nucleosynthesis, when the first atomic nuclei were formed. These early stages in the formation of matter, from the fundamental forces and particles shaped by the conditions of the early universe, are central to our understanding of cosmic history and the very matter that makes up the world around us. As the universe continued to expand and cool after the formation of protons and neutrons, it reached a temperature favorable to the fusion of these particles. During this epoch, which occurred about 3 minutes after the Big Bang, nuclear forces overcame the repulsive electromagnetic forces between positively charged protons, allowing them to combine with neutrons to form the nuclei of the simplest elements. The first hydrogen nuclei, protons, fused to form helium, as well as trace amounts of deuterium, heavy hydrogen, tritium, a radioactive form of hydrogen, and very small amounts of lithium and beryllium. The process of nucleosynthesis is very important for several reasons. First, it determined the initial content of the light elements in the universe. The proportions of hydrogen and helium formed during this time were measured in the modern universe and were remarkably consistent with the predictions of the Big Bang theory, one of the most important proofs of the theory itself. Second, these initial nucleosynthesis events set the stage for star formation. Stars that have completed the nuclear fusion cycle then form the heavier elements necessary for life and the complex structures of the universe. The importance of nucleosynthesis goes beyond the simple creation of atomic nuclei. It marked the transition of the universe from a state of simple particles and forces to a complex tapestry of matter. It was during this period that the universe took its first steps toward chemical diversity, beginning the long cosmic evolution that would eventually lead to the formation of planets, life, and the vast array of celestial phenomena that filled the cosmos. In our search for answers, we come to the next pivotal chapter in the early history of the universe, the formation of the first atoms. This epochal event, which occurred about 380,000 years after the Big Bang, marked the cooling of the universe to the point where electrons could bond with nuclei to form neutral atoms, a period known as recombination. The backdrop for this monumental shift was an expanding and cooling universe, emerging from its original state of extreme heat and density, which set the stage for the birth of atomic matter as we know it. As the universe cooled, protons and neutrons formed from quarks began to interact in nuclear fusion, creating the first simple nuclei in the nucleosynthesis stage. The nuclei of hydrogen, consisting of a single proton, and helium formed first, along with deuterium, heavy hydrogen, and lithium in minor amounts. These light elements formed the initial chemical abundance of the universe, establishing a primordial stage rich in hydrogen and helium, the simplest and most abundant elements in the cosmos. However, the universe remained too hot for electrons to remain bound to nuclei. They existed in a state of plasma of free electrons, scattering photons and making the universe opaque. As the universe continued to expand and cool, it eventually reached a temperature at which the energy of photons was no longer sufficient to ionize hydrogen. At this point, electrons began to combine with the hydrogen and helium nuclei to form the first stable atoms. This recombination process dramatically reduced photon scattering, allowing the universe to become transparent for the first time. The photons released at this point form the cosmic microwave background radiation, the relic radiation, which gives a snapshot of the universe at the moment of recombination. The formation of the first atoms was a turning point in the cosmic narrative, paving the way for the universe to transition from a hot, dense state to a cooler, structured state capable of supporting complex structures such as stars and galaxies. This marked the end of the dark ages of the universe, the time before the first stars appeared, and initiated the gravitational collapse of matter into the first stars and galaxies. These stars would later enrich the cosmos with heavier elements through stellar nucleosynthesis, seeding the universe with the ingredients needed for planets and life. Nucleosynthesis, the process that formed the natural abundance of chemical elements in stars, played a crucial role in creating the diversity of elements we see in the universe today. After the first atoms were formed, the universe consisted mainly of hydrogen and helium, the simplest and most common elements. However, the complex and diverse world around us, from the air we breathe to the materials that make up the Earth, and even the components of our own bodies, requires a much broader set of elements. Nucleosynthesis enabled the processes necessary to form these elements, acting like a cosmic furnace that transformed the pure simplicity of the early universe into a rich tapestry of chemical diversity. The process of nucleosynthesis took place in several stages and environments, beginning with the Big Bang itself. The nucleosynthesis of the Big Bang at the dawn of the universe produced the lightest elements, including hydrogen, helium, and small amounts of lithium and beryllium. However, this process failed to produce the heavier elements necessary for life and the structure of the cosmos. The next stage of nucleosynthesis occurred within stars. Stars are universal element factories, transforming light elements into heavier elements by nuclear fusion in their nuclei. During the life of a star, hydrogen nuclei burn to form helium, a process called hydrogen burning. As stars age and their cores heat up, helium turns to carbon, and in more massive stars this process continues, producing elements up to iron in successive stages of nuclear combustion, such as carbon burning, neon burning, oxygen burning, and silicon burning. However, a different set of processes is required to create elements heavier than iron, as these elements cannot be formed by synthesis in stellar cores under normal circumstances because of their energy requirements. Instead, processes such as the R process, the capture of fast neutrons, and the S process, the capture of slow neutrons, come into play, mainly during supernova explosions and in the outer envelopes of stars with an asymptotic giant branch, AGB. Supernova, the cataclysmic explosions that mark the death of massive stars, create the necessary conditions for the R process, in which a dense stream of neutrons is absorbed by atomic nuclei, resulting in the formation of many of the heavier elements of the periodic table. The S process occurs in the calmer environment of AGB stars, where neutrons are captured more slowly, allowing elements such as barium and lead to be created. The various elements formed by nucleosynthesis are eventually carried throughout the galaxy by stellar winds and supernova explosions, saturating interstellar clouds with the materials needed for the next generation of stars, planets, and ultimately life. This cycle of birth, nucleosynthesis, and death of stars, followed by the formation of new stellar systems, has enriched the universe with complex chemistry over billions of years. U-particle gas pedals are sophisticated machines that accelerate charged particles, such as protons or electrons, to high speeds and smash them together or against targets, creating conditions that mimic those just after the Big Bang. These revolutionary tools allow scientists to explore the fundamental properties of matter and the forces that govern the interactions between particles. By accelerating particles to nearly the speed of light and then colliding them, particle gas pedals allow researchers to split atomic components into their constituent parts, discovering particles and phenomena not normally observed. The operation of a particle gas pedal is to use electric fields to accelerate particles and magnetic fields to guide and focus them along a given trajectory, which may be circular, as in synchrotrons and storage rings, or linear, as in linear gas pedals, LINEX. Many new particles are produced when these high-energy particles collide, allowing scientists to study the rules of particle physics in an environment with extreme energy densities similar to those that existed just after the Big Bang. There are several types of particle gas pedals, each serving a different purpose in the field of research and beyond. For example, the Large Hadron Collider, LHC, at CERN, near Geneva, Switzerland, is the world's largest and most powerful particle gas pedal, designed to probe deeper into the mysteries of the universe, such as the properties of the Higgs boson, dark matter, and other fundamental questions about the nature of reality. Beyond basic science applications, particle gas pedals have practical applications in a variety of fields, including medicine, where they are used to treat cancer with radiation therapy and to produce isotopes for medical diagnostics, industry, for processing materials and creating semiconductors, and art and archaeology, for analyzing paintings and artifacts without damaging them. The development and operation of particle gas pedals is a feat of engineering and physics, combining advanced technologies in superconducting magnets, vacuum systems, and particle detection to explore the limits of human knowledge. These machines are not just tools for discovery, but catalysts for technological innovation, facilitating progress in many fields and contributing to society's technological infrastructure. Particle gas pedals have played an important role in furthering our understanding of fundamental aspects of the universe, and have led to many significant discoveries that have shaped modern physics. These machines, by accelerating particles to high speeds and facilitating their collisions, have allowed scientists to penetrate the deepest mysteries of the universe, revealing the existence of particles and forces that make up the fabric of everything around us. One of the most revolutionary discoveries made using particle gas pedals was the identification of the Higgs boson. In 2012, scientists at the CERN Large Hadron Collider, LHC, announced the discovery of a particle corresponding to the Higgs boson, often referred to as the God particle. This particle, predicted by the Standard Model of particle physics, is fundamental to understanding why other particles have mass. The discovery of the Higgs boson was a monumental event in particle physics, confirming a key pillar of the Standard Model and contributing to the awarding of the Nobel Prize in Physics to François Englert and Peter Higgs in 2013. Particle gas pedals also played a key role in confirming the existence of quarks, the building blocks of protons and neutrons. In the late 1960s and early 1970s, experiments conducted at Stanford's Linear Accelerator Center, SLAC, this is the first direct evidence for the existence of quarks, confirming the quark model proposed by physicists Murray Gell-Mann and George Zweig in the 1960s. It was a significant step forward in our understanding of the structure of matter, establishing quarks as fundamental constituents of matter. The gas pedals have also facilitated the study of antimatter, particles that are identical to matter particles but have the opposite charge. Experiments at CERN and other centers have allowed physicists to create, trap, and study antimatter particles such as antihydrogen. These studies are crucial for testing the fundamental symmetries of the universe and for understanding why the universe is composed mostly of matter, despite the fact that the Big Bang theory predicts equal amounts of matter and antimatter. Particle gas pedals have also enabled the discovery of many subatomic particles, including WIs and Z bosons, which mediate the weak nuclear forces responsible for radioactive decay. The discovery of these particles in the 1980s at CERN provided crucial evidence for the electroweak theory, which unifies the electromagnetic and weak forces, and was one of the key advances in attempts to develop a unified theory of the fundamental forces. In addition to fundamental discoveries, particle gas pedals have contributed to the development of medical treatments, such as particle beam therapy for cancer, as well as the development of technologies such as the World Wide Web, originally created at CERN to facilitate the exchange of information between scientists. So how do these experiments in particle physics confirm theoretical predictions? The interaction between theory and experiment in particle physics involves several key steps. Theoretical physicists develop models based on mathematical principles to explain the properties and behavior of particles and the forces that govern their interactions. These models often make accurate predictions about the outcome of certain interactions or the existence of previously unobserved particles. To test these predictions, experimental physicists design and conduct experiments using particle gas pedals. These facilities accelerate particles to high energies and then collide them, creating conditions that allow the observation of phenomena not normally available. Detectors surrounding collision points capture and record the particles produced in these collisions, and sophisticated data analysis techniques are used to interpret the results. An important aspect of validating theoretical predictions is the ability to reproduce experimental results. In particle physics, this often means that several experiments, sometimes at different facilities around the world, must observe the same phenomena under the same conditions. This repetition of results adds credibility to the conclusions and helps confirm that they are not statistical anomalies or artifacts of the experimental setup. The standard model of particle physics is a theory that describes three of the four known fundamental forces in the universe: the electromagnetic, weak and strong nuclear forces, and categorizes all known elementary particles. The model is a cornerstone of modern physics and represents scientists' best understanding of how the fundamental constituents of the universe behave and interact. The model has been developed over several decades, starting in the mid-20th century, through the collaborative efforts of physicists around the world. At its core, the standard model builds on the foundations of quantum mechanics and special relativity theory, combining them into a unified framework known as quantum field theory. The model divides elementary particles into two main groups: fermions and bosons. Fermions are the building blocks of matter that can be divided into quarks and leptons, including particles such as electrons, and the quarks that make up protons and neutrons. Bosons are force-carrying particles that transmit fundamental forces. For example, photons carry the electromagnetic force, and gluons are responsible for the strong force. A significant success of the Standard Model was the prediction and subsequent discovery of the Higgs boson, a particle that gives mass to other particles via the Higgs mechanism. The discovery made at the Large Hadron Collider in 2012 filled a crucial gap in the model and has been hailed as one of the most significant advances in physics, confirming the existence of the Higgs field and its associated particle. Despite the successes, the Standard Model is not complete. The model does not include the fourth fundamental force, gravity, described by the general theory of relativity, nor does it account for dark matter and dark energy, which appear to make up the majority of the mass and energy of the universe. In addition, the model's inability to account for gravitational forces or predict the masses of elementary particles suggests that it is part of a more complete theory that has yet to be discovered. While the Standard Model of particle physics is an extremely successful theoretical framework, it also has its limitations, marking areas where our current understanding of the universe is incomplete. These limitations not only emphasize the limits of the model's applicability, but also point to new physics beyond what we currently know, guiding researchers in the search for a more complete theory of fundamental forces and particles. One of the most significant limitations of the Standard Model is its inability to account for gravity. Gravity, as described by Einstein's general theory of relativity, is the fundamental force that governs the structure and dynamics of the cosmos on the largest scales, from the orbits of planets to the evolution of galaxies and the universe itself. However, the Standard Model is based on quantum field theory, which naturally does not include gravity. This contradiction between large magnitude, general relativity theory, and small magnitude, quantum mechanical theories, is still one of the most important problems in physics. Another limitation is the Standard Model's silence on the nature of dark matter and dark energy. Observations of the universe show that about 85% of its matter is dark matter, which does not emit, absorb, or reflect light, and is detectable only by gravity. Dark energy, which accounts for about 68% of the total energy content of the universe, is thought to be responsible for its accelerated expansion. However, the Standard Model does not predict the existence of dark matter particles. It also fails to explain the properties of dark energy. So much of the universe remains unexplained. The Standard Model also fails to explain the matter-antimatter asymmetry observed in the universe. According to this model, the Big Bang should have produced equal amounts of matter and antimatter, which should have annihilated each other, leaving behind a universe full of radiation. However, the observed universe is dominated by matter, indicating that processes not considered in the Standard Model should have given matter an advantage over antimatter. The Standard Model does not provide a satisfactory explanation for the mass of neutrinos. The model originally assumed that neutrinos had no mass, but experiments showed that they have a small mass. This discovery necessitated a revision of the model, and also opened new questions about the origin of neutrino masses and their role in the universe. The Standard Model is a collection of particles and forces without a unifying principle that can explain why this collection of particles and forces exists. The main goal of theoretical physics remains the search for a theory of everything that unifies all fundamental forces, including gravity, and provides a deeper understanding of the particles themselves.